So last class basically discussed on your shear force diagram and bending moment diagram. So now today I have got to discuss as a cantilever beam. So how to draw the shear force diagram and bending moment, and basically you have to use here as uniformly distributed load is not symmetrical. So suppose you have to solve the problem as a cantilever beam as uniformly distributed load is not symmetrical. First of all, so what is your problem? So now today so second problem, a cantilever beam of length 5 meter carries load as shown in figure 1, figure A. Draw the shear force diagram and bending moment diagram. Okay. So how to solve this type of the problem? So now this is your one cantilever beam. And you have to apply the load at the end of this beam. And then after, you have to apply uniform distributed load. So already previously, so we have to teach you what is uniform distributed load. So various type of the loads. One is the concentrated load, then after uniform distributed load, then after your varying load. As a concentrated load, somebody have to say here as a point load. And previous class, we have to solve the problem a concentrated load. So now today I have got to solve the problem this cantilever beam and uniform distributed load. So from here to here your distance is 2 meter. And then after your from this point to this point your distance is 3 meter. So now put here the value. This is your 2 meter, and from here this is your 3 meter. And now at the load, so load is your 20 kilonewton, and uniform distributed load is your 6 kilonewton per meter. So how to compute the shear force diagram and bending moment diagram in this problem? So first of all, so you have to the big challenge to how to compute the uniform distributed load, and you have to convert as a concentrated load. So this is your uniformly distributed load. This is your uniformly distributed load is not symmetrical. So first you have to solve and know about what is the procedure. You have to solve this type of the problems, uniform distributed load. and how to you have to draw here this load diagram to as a equivalent load diagram. Then after you have to solve shear force diagram and bending moment diagram. So now first I am going to discuss here in these positions. So how to solve uniformly distributed load is not symmetrical. Then after go to solve the. So suppose I have take one example as a, this is my reaction force RA and another is your reaction force as a RB. RA and RB, and you have to apply a uniform distributed load. Uniform distributed load. Okay. And then these locations, so I will simply written down here here to here is your length. Suppose I will say L, and then again so written down from here to here, the length is your L1, and then again from this point to this point your length is L2. So your length is L2. And your uniform distributed load, so just I have to written down here the W. As per W is your kilonewton meter. Suppose L1, L2, L1 and L2 is your meter. So I have to solve here one problem, distributed load. Is not symmetrical. So how to compute of your reaction force as a RA and RB? So first of all you have to draw an equivalent load diagram. So how to draw the equivalent load diagram? So draw equivalent load diagram, placing the equivalent here, placing the equivalent load at the centroid of the distributed load. So the centroid of the distributed load. So simply, so I have draw here one equivalent. So this type. And what is the length from here to here, total length? So this is your equivalent load diagram. So I go to draw here equivalent load diagram. Equivalent load diagram. So this is your basically load diagram, here the load diagram, and the next is your equivalent load diagram. So first of all you have to draw the equivalent load diagram, placing an equivalent load at the centroid of the distributed load. So this is your centroid of the distributed load. So then how to compute the distance from here to here? So basically this is your L1 and the next word is given the other centroid of the distributed load. So the length of from this point to this point is our LO plus L1 by 2. L1 by 2. L1 by 2. Okay, so this is RA, RB, RA, RB, and you have to apply here the load W. So then after, very easy, you have to compute the reaction force at RA and RB. Okay, very easy, you have to compute the reaction force as a RA and RB. And here is the W. As per the unit, W is, suppose I will say here the unit is my kilonewton, and here is your W as per unit is kilonewton per meter. Okay, so you have to apply here the uniform distributed load as a W, kilonewton per meter square. And here is, you have to convert as a concentrated load as equivalent load diagram. So you have to, your unit is convert as a W weight, W kilonewton. So now to compute this process in a very simple manner. So how to compute? The equivalent load W is equal to what your? So equivalent load here W. So equivalent load your W is equal to what? Equivalent load W is equal to your, so W multiple of this value. L1 divided by L2. So how? So W is your kilonewton meter. Just you have to watch as per the unit, kilonewton per meter. And here is the your, this W, sorry. So this W is my kilonewton. And here is your kilonewton per meter. This W is my kilonewton per meter, and then after go to the multiple here as a meter, So this length as a meter. So this meter and this meter have go to the cancel out, and now you have to compute the equivalent load condition. And already, so all things are previously discussed in the previous problem, how to compute the RA and RB. Suppose you have to watch here the procedure how to compute the RA and RB. So first of all, so I have just input here the one value. Then after, so I go to the compute here the process. So I will input here. So W will be equal to, so our just assumptions, W will be equal to our 800 Newton per meter, and then after your RA you have to compute what is the value of RA. Then after your RB you have to compute the value of RB. So what is your RB? Then after your L, suppose I will say here L is our 0.8 meter, and then after L1, so L1 is equal to, also input here the 2 meter, and then after L2, so L2 will be equal to your basically 3.2 meter. Okay, so just you have to substitute the value of this process. So compute the RA and RB. So how to compute? So you have to use this process, equivalent load diagram. So first of all, you have to go the equivalent load. So what is our this capital W from this way? So discuss in the process. So our capital W. So W will be equal to your our 800 Newton per meter. Then after come to the multiple of. So what is the length here? So the length here is your L1. L1 is the 2 meter. So L1 is the 2 meter in the sense of in the symmetric L by 2, L1 by 2. So multiple here the your 2 meter. So 2 meter, and then after your W will be equal to of your 1600 Newton. So now this meter and meter have go to the cancel out, and W equal to your 1600 Newton. Okay, so this is your basically from this positions of 200, sorry, this positions of your 1600 Newton. So now after compute the value of your basically this process, what is the reaction force? So how? So we have to use, so just come to, so I am explaining here how this W is calculated here. The load distribution run as 2 meter, so run as L1 is the 2 meter. So the location of the equivalent load is, 1 meter in the centroid. From here to here, the center is 1 meter. From the left end and distributed load, So our 1.8 from A. So L plus L1 by 2 is your basically 1.8. Okay. So now come to the equivalent load of W will be equal to your basically in the 800 Newton multiple your 2 meters, and this Y I will written down here the 2 meter. So basically your divide by this multiple. So Y written down here 2 meter from distance from here to here, and then after your divide here 1 meter. 800 Newton, then after your divide by 1 meter from here, just watch. So this is your 2 and go to the center, this is your 1 meter. So also you have to write down here and the same manner 1 meter. Second thing, so first I have go to directly compute the value of 800 Newton multiple of your Newton per meter multiple of the 2, and then after, so second number process I have got to use here the 800 multiple your simply Newton, so this is the Newton, and then 2 meter divide by 1 meter, 1 from L1 by 2. So, okay. Now next things you have to compute the value of the moment. So how to go to the compute here the moment. So taking the moment about 0.8, the next is your taking the moment about taking the moment about. So RA multiple 0. So 0. Then after your downward direction, so I will say here the minus, and the what is the total distance? L plus L1 by 2. So L is our 0.8 and L1 by 2 is my 2. That means here 1. So total distance is our 1.8. So W is our basically minus 1600 multiple of 1.8. Then after come to here, so upward direction is by RB. RB is multiple of your L plus L1 plus L2. 0.8 and 2, 2.8, 2.8 and 3.2. So basically your 6 will be equal to your 0. So now compute here RB. RB is equal to your minus 1600 multiple of, this is your 1600 multiple 1.8 and divide by 6. So your value is 0.3. So now RB equal to 480 Newton. 480 Newton. So this is our RB, 480. And then you have to compute here the value of RA. So what is your RA? So come to the equivalent diagram and equivalent load diagram, and again you have to solve here as a equilibrium conditions. So what is the equilibrium conditions? So our equilibrium conditions is RA minus 1600 Newton plus 480 will be equal to 0. So your Ra equal to is basically 1120 Newton. So compute this value, 1600 minus 480, so 1120. So through this procedure, you have to compute the value of Ra and Rb, so equivalent load diagram. So you have to implement this process of this problem instead of this problem. Then after you have to draw the shear force diagram and bending diagram. Okay, so now come back on this problem. So how to compute in my cantilever beam of length 5 meter carries load as shown in figure A, drawn the shear force diagram and bending diagram. So for computing shear force, so I go to solve this problem. Computing shear force. A number point, our 0 is less than equal to x less than equal to 2. So I am going to discuss compute here the shearing force diagram SFD and use here the first section from this first section from here to here, first section. Okay. So what is your force? So force equal to you have to watch. So I am using here the global coordinate system. So x-axis is the positive and this upward side the y-axis is the positive, but the symbol is the downward directions. So I am using here the minus 20 kilonewton. So first section, the very simple you have to compute. But go to the second section. So our 2 is less than equal to x less than equal to your 5. Total length is your 5. Total length is the 5. So what is your force equation? So force is equal to your first of all minus 20. Then after go to the minus, and then you have to use here the 6. Then x minus 2. So why I have written down here the 6x minus 2? So already discussed in the previous procedure on this problem. Just already I will discuss on this problem. So why I will written down here minus x by 2. So minus 20 minus 6 minus x by minus f is equal to minus 20 minus 6 x minus 2. So now compute the value. So what is the equation? So f is equal to your minus 20 minus your 6x, then after come to here your plus 12. So force f is equal to your, that is minus 6x then minus 8. So at x is equal to your 2, then force f equal to your minus 20 kilonewton. Just you have to watch. So f is equal to, so minus 12 minus 8, and at x is equal to your 5. So your force equal to your minus 30 and minus 8. Minus 8 equal to your minus 38 kilonewton. Minus 38 kilonewton. So from the equation number 1, you have to solve this problem. So now come to draw the shear force diagram. How to draw here the shear force diagram? Through this process, so I compute here the value of force at point. Suppose I will say written down here the A, B and C. So here is our A, this point is our B, and here is our C. So just extend this line. Then our value is here. Just you have to watch. First, when you're at point A, the force is your basically minus 20 kilonewton. So you have to draw here minus 20 kilonewton from here to there. So this is your minus 20 kilonewton. Then after, so your value is come to here as a 20 kilonewton to 38 kilonewton. That means, so here your force as linearly varying here. The force is linearly varying here from 20 to 38 kilonewton. So the force, so here is your minus 38 kilonewton. Okay. So through this process you have to draw here the shear force diagram. This is your SFD. The next you have to draw the bending moment diagram on this problem. How to draw the BMD. So next step I have got to solve here the bending moment diagram. So one another things you have to just go to here. So observe that the maximum shear force is minus 38 at the fixed yield and is negative in nature. So just you have to observe this problem. So what is the maximum value at your fixed yield? Okay. So then next come to the compute your bending moment. For computing, bending moment. Now so first A, so for computing the bending moment, 0 less than equal to x less than equal to 2. So what is the equation of moment? So moment will be equal to your minus 20x. So at x is equal to 0, so your moment equal to 0, and at x is equal to your 2, so your moment equal to minus 40 kilonewton meter. First number equation. Then after come to the second number equations, from B 2 less than equal to x less than equal to 5. So our moment equal to, I will written down here, so minus 20x. Then after come to here the minus 6x minus 2, 6x minus 2, and then multiple of your x minus 2 divided by 2. X minus 2 divided by 2. So uniform distributed load apply at the centroid of these positions. That means your x minus 2 divided by 2. So you have to cancel out from this manner to this. So this is our 3. Then the moment equal to minus 20x, then minus 3 x minus 2 square. Compute the moment. So at x is equal to 2. So what is your moment? So moment equal to my minus 40 kilonewton. Minus 40 kilonewton meter. And when you have to substitute the value of at x equal to 5, so my moment equal to your minus 20 multiple x, that means your minus 100, and then minus, so here is your 5 minus 2 3 square, that means your 9 multiple 3 27. So moment equal to your minus 127 kilonewton meter. So now next, so I go to draw here the bending moment diagram. So again draw a line and extend this line from okay. So now watch here. So moment is your first case, the minus 40. So 0, m0 is 0. So here is our 0. And then after come to the minus 40. So this is your linearly varying here. And then your uniform distributed load. And your moment is the minus 127 kilonewton meter. So here is your point. Suppose I will say is our minus 127 meter. So how to draw here the curve? So this curve is the convex and the curve is your upward direction, otherwise downward directions. How do you have to watch and how do you have to draw here this curves from this point to this points? So just simple, I draw here a curve and explain you. So this curve is the convex is upward direction, otherwise this curve is the downward direction. So now here is your 0 kilonewton meter. Then upon to this point, point B is our minus 40 kilonewton meter. And at the point of the C is our minus 127 kilonewton meter. So next things, so how to justify and how you have to decide. So this point, this curve is our convex and upward direction or as a downward direction. So first of all, justify here the observation of the shearing force in the following point. So first I go to the observe here. So observation of the following points. So in the shearing force diagram of this figure, there is a sudden change at slope at x is equal to 2. At x is equal to 2. Okay. Beyond which a distribution load is applied. And the second thing, in the bending moment diagram, figure C here, there is no sudden change in slope at x is equal to 2. And the third number come to discuss on this point. The next point, in the observation of the bending moment diagram. So here, so I am discuss here. So some students may get the confusion whether the bending moment curve between the x2 and x5 will be convex upward or downward. This convex is the upward or downward. For them, it is advisable to find the bending moments. So if the value is less than the mean of the value at x equal to 2, at x equal to 2 and x is equal to 5. So go to the compute here the mean value. So this compute here the mean value of x is equal to at x is equal to 2 and x is equal to 5. Then the curve is upward, otherwise it would be downward. So first of all go to check here as a mean y. So this curve is upward and downward. So what you have to do there? So this is your equation, m is equal to minus 20x minus 3 multiple x minus 2 whole square. So I am using here at x is equal to mean value, suppose I will say here 3.5 meter. So 3.5 meter. So this is your 2 and here is our 1.5. So 2 plus 1.5, I go to the mean position, mean in the center lines here. So as I compute the mean condition, so what is the value on this position? So substitute the value of at is equal to 3.5. So moment m equal to your basically minus 20 multiple of your 3.5, then minus your 3 and multiple of your basically, so I will change here the symbol multiple, so some confusion. Okay, and this value is 3.5 minus 2 in the sense of 1.5 square. So moment will be equal to your 3.5 in the sense of 70. This is your minus 70, then minus your 1.5, that means 3 multiple of 2.25. So m equal to your minus 6.75 here, so minus 76.75 kilonewton meter. So this positions is your minus 76.75 kilonewton meter. So after the computing the mean value, so your value is here minus, so hence your this curve, convex curve in my this upward directions. So suppose your value is some come to here in the sense of this position, so your point is here, that means some compute here this position, then you have to find out, so which type of you have to draw the curve. So also you have to check the value. So suppose at is equal to 4, x is equal to 4, s is equal to 4.1, x is equal to 4.2. So the curves are generated according to this manner. So your curves are not generated in this manner. This is the wrong procedure. Okay. So now, so thank you very much for attending my class. So if any of the confusion, if any of the doubts after completing this course topics, then very easy you have to ask me. So